Okay, thank you. Thank you, Pierre, for the invitation. I just arrived here yesterday. I'm going to be here for 2 weeks. It's very exciting. So I'm going to talk about computing Kazhdan constants by computer. So it's experimental mathematics talk. I'm going to present you some numerical results. I'm not going to prove any theorem, but I see many mathematicians in the audience. I try to say something about mathematics too. So let me start with the definition. I'm sure you know better than I do. So property T is a property of a group defined by Kazhdan. So the good reference book is the book by Becker de la Valette, the Kazhdan property T. And the property T is a very useful property, which is used in many things, proving rigidity, fixed point theorems, producing expanders by Margulis, and also having a very good mixing property in ergodic theories. And also I heard there are some good applications in C-star algebras too. And in this talk, I only talk about discrete countable groups, and which is going to be finitely generated. Also, it's going to be it's also defined for Lie groups, but I'm just talking about finitely generated group. Examples of groups with property T. First of all finite groups have property T. And also among infinite groups, SL and Z and at least 3 have property T. And also, once you have a group with property T, any of its quotient has property T as well. Examples of groups without property T, I start with Z. And then, because of the property I just mentioned, any group which has a quotient isomorphic Z doesn't have property T. For example, Z to the n, and any free groups don't have property T. And also SL to Z, it doesn't have a Z quotient, but it doesn't have property T either. Okay. Unknown cases, famous cases, O of Fn, and at least 4. Some people think they do have property T because there is some good mixing property associated to this group, so they believe it's a consequence of property T of those out of Fn or out of Fn. Okay, so this is a brief introduction of property T. Now here's a definition of property, a group with property T, or a Kazhdan group. This is a numerical definition defining the Kazhdan constant. So here's the definition of Kazhdan constant. Suppose you have a group gamma, finitely generated, with you fix one finite generating set S. And now if you have any, so you can say also one representation pi, then you can define this number kappa by this formula. So first, you take any unit vector, try to move it by this finite generating set, and you do it as much as possible. Then you take inf over all unit vectors. So that's this number kappa. Then now you look at all unitary representations without any non-zero fixed vector. Then that's the Kazhdan constant of gamma for this finite generating set. And if this number kappa is positive, then you say this group has property T, and then this number kappa is the Kazhdan constant of this group gamma with respect to this generating set S. And this property being kappa being positive doesn't depend on the choice of S. So it's a well-defined property for the group gamma. So for those who are not familiar with this thing, so in words, it means kappa is a Kazhdan constant if you are given any unitary representations without any fixed vector, if you are given any unit vector C, you can move. There is one generator in the fixed generating set that moves C at least by kappa. Okay, so that's a Kazhdan constant, and this is the Kazhdan constant after you take inf. But any constant at most kappa, some people call it a Kazhdan constant. All right, so this is the definition. But I'm not trying to compute this Kazhdan constant, but what I'm trying to compute is something else which is closely related to the Kazhdan constant. Okay, so that's going to be the spectral gap of the Laplacian of the group associated to the generating set S. So this is the definition of Laplacian for the group gamma with the given generating set S. So mathematically, it's just one element in the group ring of gamma. Okay? So group ring is this R gamma. So R gamma is something like this, in case you are not familiar with this. So just take a finite collection of elements in gamma, put some weight on each element in that collection. So that's going to be an element in the group ring. But if you have two of those, you can add, and also you can multiply using group structure of gamma. So that's, in that way you get a ring. That's a group ring. So this is just one element in the group ring because you put weight -1 on each generator, then the weight, the cardinality of S to the identity element. Okay? So that's the Laplacian, which is just one element in the group ring. But also you can see this Laplacian on the Cayley graph. So you have a group gamma, finite generating S, you form the Cayley graph, and you look at the function on the set of vertices, then you can sort of average along the neighborhood this, at each vertex, and then so you get another function from a function you were given. So that's a Laplacian operator. So you can see it that way too. Now, if you are given any representation pi, you get the operator for the Laplacian, because if you have a representation, any element, for any element you get the operator on the Hilbert space, but now element in the group ring is just a collection of finite remaining elements with weights, so you can just add and multiply and add and you get one operator for the Laplacian operator. All right. Now the spectral gap of the Laplacian. So for those like me who are not familiar to function analysis, you can see this Laplacian is like a matrix, a symmetric matrix with real entries. So you can diagonalize and you get real eigenvalues. And then look at the smallest eigenvalue of the matrix. So that's going to be the spectral gap. So it's in functional analysis, it's going to be infinite dimensional space, but so this is the smallest, well, it's not exactly eigenvalue, but spectrum of the Laplacian, pi gamma, pi delta, and epsilon is the bottom of the spectrum. Okay. And we call it a spectral gap. So now this is an important connection between the spectral gap with the Laplacian and the Kazhdan constant. So this is an inequality you already have. One way to see this inequality is it gives a lower bound of the Kazhdan constant using the spectral gap. So clearly, if the spectral gap is positive, then kappa is positive. Therefore, the group has property T. But also, in fact, the converse is true. If the group has property T, by definition, it has positive kappa, and in fact, this spectral gap is positive. So this is what I said. So epsilon being positive and kappa being positive is equivalent for any finitely generated group. And I call it basic inequality in this talk. This epsilon is a number I try to compute, or at least I try to give a lower bound to. Okay. For that, I use this very nice theorem by Ozawa. So this part is his theorem. So let me just read. Okay. So this is a equation in the group ring. Okay. So left-hand side, delta, as I told you, is an element in the group ring. So delta square is another element in the group ring. Epsilon is a constant. So the left-hand side is a group element in the group ring, depending on epsilon. Okay? Delta is fixed because you fix gamma, the group, and generating set S. So delta is just fixed, and epsilon you can vary. The right-hand side, Bi is an element in the group ring. Star operator I didn't define, but it was here. So it's some operator. You can, first you know this star is, you can see that the right hand side is the sum of squares, the square sums in the group ring. So in this equation, epsilon, the number, and Bi's element in group ring are unknowns. We are supposed to find the solution for that. And he says, if you find the solution, a pair epsilon and Bi's with epsilon positive, then your group has property T. And that's if and only if. Okay, that is what the theorem says. Okay, so let me say a little bit more about this equation. So rough idea. So remember the definition of the spectral gap. This is the definition of the spectral gap epsilon. Okay. So suppose you have a positive spectral gap epsilon, then I keep using this analogy to the eigenvalue of a matrix. So the smallest eigenvalue is epsilon. Okay. Therefore, delta square minus E delta is non-negative, right? Because imagine this delta is just a number. So this delta is bigger than this epsilon. Of course, this delta square minus epsilon delta is non-negative number. But in fact, this is an element in a group ring, and there is a well-defined notion, non-negative, in group ring. So this implication is justified in that way. But now this direction is really his theorem. So once you have suppose this is a number and a non-negative, it's a square, right? You can always have a root, square root. But his discovery is that in the group ring, if an element is non-negative, in fact, it's a square sum. Okay, this is what it says. So if epsilon is a spectral gap positive, then delta square minus epsilon delta is non-negative or positive. Therefore, it has to be a square sum. Okay. So this is a rough idea behind this theorem. Moreover, you try to find a solution in the real group ring, but in fact, if there is a solution in the real numbers, he says there is a solution in Q's too. Okay, this epsilon is in the rational number, and also the coefficient of the Bi's in the group ring is also Q's too. Okay. So now you see the chance that there is algorithm which computer can do, because now your group gamma is a countable group, and you just look at the group ring with Q coefficients, so it's countable, and epsilon, again Q, so it's countable. So you just plug in all possible BI's and epsilons and see if this is true or not. So, and his theorem says if gamma has property T, eventually you find a solution. Okay? And also, if it doesn't have property T, you never find a solution. So it's really a semi-definite algorithm for you to be able to tell if the group has property T or not. Yeah, and then also it turns out the soup of the epsilon for a solution is same as the spectral gap I defined in here. So this epsilon is exactly the same. So you try. So once you find the solution, you try to look for another solution with a bigger epsilon. So that's going to be the spectral gap of the group. So here's a summary of what I'm going to do in computer. So given a group G, try to solve his equation, this one, and if you find a solution with positive epsilon, you are done. The group has property T. And after that, to get the better constant epsilon, try to maximize epsilon. And now remember this basic inequality which always hold. Plug it in here with positive epsilon, then you get a nice positive lower bound of the spectral, the Kazhdan constant kappa. Okay, this is what I do for some examples. So as I said, in principle, if G has property T, there's going to be a solution. Otherwise, it's not going to stop. And also, I'm not sure if you're interested in this part of the talk or the work. This kind of question fits nicely in so-called optimization problem by SDP, semi-definite programming. So there are many specialists doing this kind of SDP using a very strong computer. Before I go into some examples, I mentioned one point when we are searching, for a solution. So I try to find a solution for this equation. Okay? And BI is an element in the group ring. And remember, element in the group ring is just finite collection of elements with some weights. But maybe I call this finite collection of elements for each group ring element support, or since I'm fixing the generating set, you can talk about the biggest word lengths in the support. So I call it just the range or the support of each group element. So you try to find a solution, but of course you try, from the beginning. Therefore, what do you do if you're doing by hands? First, you look at element in group ring whose support is only on the generating set, okay? And vary the coefficients. And next, maybe you look at the elements of word length 2 and vary the coefficient on that element, and so on. So the SDP, what SDP can do is that once you fix the support of BIs, then not only they can find a solution if it exists, but also they can maximize this epsilon 2. Okay, so in that support range I fix in advance, they can really find the best solution for epsilon. And if they don't find a solution, it means there is really no solution in that range. So I start increasing the range, bigger and bigger support. So this is what I do. Okay, this is what I'm talking about. And in reality, so D is the max of the word length. 4 is a maximum. I sometimes succeed, I sometimes don't, because I don't know if you ever pay attention to these kind of things, but imagine, for example, set of generators, the cardinality is, say, 10. You may think 10 is a large number, but it is not. For example, SL3Z. Okay? So how many elements do you need to in elementary matrices? So you need 1, 2, 3, 5, 6, 7. Sorry, 1, 2, 3, 5, 4, 5, 6. But in fact, in this approach, S star has to be closed under taking inverses. So even for SL3Z, you need 12 elements. And now the word length D means 10 to the 12 to the 4th. And in fact, you are multiplying two elements, so it doubles like this. So it's already 10 to the 8th. So it's a large number. Computer can deal with only like 10 to the 10th at most. Okay? So, I mean, you can just say, look at the ball of radius 10. It's really impossible for computer to deal with. So that's the issue. Okay, so this is the algorithm. I repeat again. But there are three reasons why algorithm doesn't stop. First, G doesn't have property T. Then they never find a solution. Second, G has property T. Therefore, by theorem by Ozawa, there must be a solution for this Ozawa equation. But when I try with computer, I have to fix the range of BIs, support of BIs. So maybe there's a solution, but there is no solution in that range. And then, as I told you, I can't have D to be 10 or something. So in that range, there's no solution. Or the third case is that maybe there is a solution in that range, but computer is not strong enough, memory is not big enough. Yes?
Theoretically, this algorithm would always stop if you had a big enough computer, is it though?
You're asking if it's going to stop or not?
No, I mean, with an infinite computer, are you saying it's a...
Provided it's
T. It shows that T groups are recursively enumerable.
Yes, if you have a very good computer, yes, the group has property T, then eventually you find the solution. Yes, that's what I'm saying. Yes.
As far as I remember, this is the first.
Little issue. Even if the group doesn't have a solution to our problem, because so I make one technical comment before you ask. So I'm not using the solution of word problem, because you may say, you have to, here you are multiplying group elements, so you have to know, after you multiply two elements, what is the element you get. So you may think you have to know the word problem, okay? But some group doesn't have a solution for word problem, but it's okay, because I'm just claiming the semi-definite algorithm. So if you have a semi-definite algorithm for the word problem, you're okay. So I'm making some point, but I don't know. Okay. Anyway, yes, you have a very super computer, you'll be okay. Yeah. Okay.
How do you, for the coefficients of the bit heights, how do you choose? Because they are rational numbers, right? So in your algorithm, you start with the initial coefficients and then go down to the denominator.
Are you talking about really what I'm doing in computer?
Yeah.
That's part of SDP. So I really don't know what they are doing, but they are not doing, like you start with Z's and then next Z over 2. They are not doing that, I think. It's in the package of optimization problem. Do I answer your question?
Isn't it because of the nature of the sort of constraints that somehow, an extreme value has to be rational in some sense? stored in the STP setting. Maybe that's not. I guess it's not linear.
So can you remark? Can you say again what's STP?
What SDP is?
What is STP in general?
What is SDP in
The
general?
software produce an approximate solution.
Yes.
They don't claim to give you the real coefficient optimal solution. They process by successive approximation. And they stop at a certain precision, right? That you specify in advance.
Okay,
It's
so
a numerical approximation, optimization.
It's
numerical
an iterative
optimization.
algorithm.
yes. Anyway, it's a numerical approximation, but I think that's not what you're asking, right?
So this means that you are actually not concerned about the fact that you can actually find rational solutions.
Everything is going to be rational.
Right. So if computer says I found a solution, rational solution, I don't trust him because it's just approximation. So if I plug in, maybe the difference between the right hand side and left side is really, really small. But okay, there is a math part. So but the math part is that if you find an approximate solution, actually you can guarantee there is a solution. So there is one lemma, mathematical lemma. So that's one thing. Okay. But I think you are asking something different. Did I answer that?
So, okay, so but maybe this is what you're saying. So you're saying that you get an approximate solution, and then there is this mathematical lemma saying that guaranteeing that there exists a solution. That
Yes.
you actually not this algorithm is actually not giving you the solution. What solution?
Okay. My human algorithm. So so his theorem says if gamma has property t, if and only if there is a rational solution. Okay. But now I have a collection of rational candidates. I just plug in one by one, keep going, and for rational candidates, you can exactly say, if you know about problem, if this equation holds or not. Okay. In that sense, mathematically, I will find a solution.
Yeah, I agree.
You agree? But a computer, first of all, SDP is not doing that. It's not doing, okay, you're plugging all possible ones. So they are doing something else, first of all. Second of all, whatever they find is just approximation. So there are two things.
So in practice, you're not going to get your hands on some exact solution. But the computer will, using the computer, you'll still be able to say that there is a solution.
For him, yes. So he says, okay, here's a solution for you. So I really get the, concrete BI's and concrete epsilons. But in fact, that's just approximation. If I plug in, maybe it's not exactly true. Yeah.
But then it doesn't matter for you because you know that it implies that there is a solution.
Yes, if this approximation is good enough, then there is a solution.
And
Yes,
epsilon
that's
is-
math.
The epsilon it produces will be really close to the actual solution.
Yes.
No,
So that it
Yes.
will be smaller.
What?
So that it will be smaller maybe.
Yes,
Somewhere
yes,
further.
yes. So it could happen that he says he found a positive epsilon, but if I apply this mathematical lemma, it's no more positive. It can happen. Okay, so let me go on. So what time shall I start?
You still have half an hour.
Okay, like 10 past, no, okay. Let me, okay, so this is a part. So in fact, that lemma, which guarantees exact solution, once you have find a pretty good solution, is due to Netz and Tom. So I say, so the value, computer finds a numerical solution for epsilon, and after I apply Netzer-Tom lemma, and if I still get a positive epsilon, I say it's certified value. It's really a mathematical thing. You can really trust it. Now that was the end of the first part. Now I try to present the numerical results. So the example I tried is a group acting on A2 tilde buildings. So A2 tilde building, by definition, is a two-dimensional, simply connected, simplicial complex such that the link of the vertex, which is a graph because it's two-dimensional, the complex, the link of any vertex, the incident graph of a finite projective plane. But if you're not familiar to this kind of things, it is okay for you. I draw one easiest example of the incident graph of a finite projective plane, which is this graph. Name is Heawood graph. So there are 14 vertices. It's a bipartite, so 7 blue ones and 7 red ones. Smallest or a loop has length 6. So in particular, this A2 tilde building is a Cat0 complex because it's two-dimensional simplicial complex. So every cell, biggest dimensional cell is a triangle, and you patch them together so that the link of each vertex is, for example, this graph. Okay, so the shortest loop has length 6. And you put 6 triangles together, you get satisfy this local Cat0 property. In fact, so there is a way for you to produce finite projective plane. You start with a finite field F with Q elements, and then form the three-dimensional vector space and look at one-dimensional subspaces and the two-dimensional subspaces. Then there is an inclusion, etc., and you can produce a finite project plane, and the incidence graph is really with respect to this inclusion incidence. But most part of the talk, you can just have this picture in your mind. Okay? Just a two-dimensional simplicial complex whose link is maybe always this one. Okay. Now here's a theorem by, I think, Pierre. If you have a A2 tilde building, and suppose you have a group acting on it properly and co-compactly by automorphism, then this group has property T. Moreover, there is a way to choose a finite generating set S so that Kazhdan constant has a uniform bound by this number. This number Q is, remember, in the definition of A2 tilde building, the link was a graph. And for example, this one, so that I should have said, the order is a number of elements in the field. In this case, the field was just 2 elements, so this order is 2. So, for example, if you start with A2 tilde building, whose link is that Heawood graph, then your group G acting on X property and co-compactly, it's not only Kazhdan group, and also there is a generating set S so that Kazhdan constant is at least this number with Q equal to 2. Yes.
But there is a Cartwright-Montgomery's figure where they compute Kazhdan constant explicitly, like.
Yes, in the next slide I'm going to talk about it. So I think this was first proved by Pierre, and then Zook proved a version for, I think, bigger class of groups and spaces, and also Ballman, Swiatowski proved another version. But I like to make a point that this bound is only for particular generating set S. Okay? And also, I'm not saying this number, even for that particular generating set S, this number is not exactly kappa, it's just give a lower bound. Okay? But as she mentioned, in fact, in some very special cases, this is a Kazhdan constant. Okay. So that is going to be the theorem. So for that, I have to introduce another thing, which is A2 tilde group. So I wish a group acting on A2 tilde building, the lattice is A2 tilde group, but it is not. It's much more restrictive. So A2 tilde group is acting on A2 tilde building, so that action on the set of vertices is regular. That means free and transitive. So so maybe for me the best way to describe this group is not exactly the definition, but if you have A2 tilde group for some choice of generators, your Cayley graph is exactly the one skeleton of the A2 tilde building. So your Cayley graph is really A2 tilde building. In other words, if you have a Cayley graph, you form the flat complex, putting in squares, then you get the A2 tilde building. Then your group is A2 tilde group. And then those people proved that, computed and proved that Kazhdan constant is this number. Again, this Q is the order of the instance graph. So I go back again. So it has a different expression, but for A2 tilde groups, the equality holds here. Okay, this number and this number after you plug in this number is same. So the summary is for A2 tilde groups with a very special generating set, you know the Kazhdan constant. By the way, as far as I know, this is the only class of infinite groups where the Kazhdan constant is computed. And in fact, A2 tilde groups has been classified for small order. In fact, for 2 and 3, it's completely classified. And for Q is 2, in other words, so the link is really this one. Okay, so you have a 2-dimensional complex, K0 complex. The link is this one. And by chance, you have a group whose Cayley graph is exactly the one skeleton of that complex. And in fact, there are only 8 of those. In fact, there are only 7, there are 9 of those, but in fact, A1 and A1 prime have the same groups, but different presentation. So there are 8 or 9 groups of A2 tilde groups with order Q equal to 2. For that one, we know the Kazhdan constant by this one. Now I did a computation, and this is a numerical solution, which is supposed to give a lower bound of kappa, but it was exactly the same. So this numerical lower bound, I don't know, by chance or whatever, is exactly the Kazhdan constant. So this certified bound is exactly addressing that issue. So this is just computer, the number computer gives. So I have to certify mathematically. So those value, the value I can certify for you as a lower bound of kappa. So it gets slightly smaller. So it's not exactly same as those ones anymore, but still I see it as a good sign or evidence that if you find a solution, in some cases, in fact, you are really having the spectral gap. Okay.
So there is equality between spectral gap and square root of 2 epsilon, right?
In this case, yes. In this case, yes. This is, okay, they didn't mention that, but you are right. So in these A2 tilde groups, in this basic inequality, there is equality. So you are right. So we can only find, at the best, this part. Okay, because we are just computing epsilon, we're not computing kappa. But in some cases, in fact, this is same, and that's what it seems happened here.
There is a reason for this? Quite surprising.
Okay, I don't know. So later you will see. Okay, so I tell you in advance. So this is the only class of infinite groups where kappa is computed. By chance or not, there's equality in this basic inequality. There is few other cases where Kazhdan constants are computed for finite groups. Only finite groups. Of course, finite groups always have property T, but it's completely different issue. If you really compute the Kazhdan constant, in that case, spectral gap is also computed, and there is really a gap between those two numbers. Okay, so I don't know why there is equality here, and so I don't know. Okay, so in the case order is 3, there are many more groups. I didn't try all of them, but I started with the first class of groups on the list, and as you see, it's same. We again, so our numerical solutions is exactly identical.
What's the first column?
So I apply Nexo term.
The first one.
This one. This is how they classify. Nothing. They okay. I don't know what 1.1 is for. Okay. There is a classification, and there are lots of tables. So this is the first class of groups in this category. So I don't know what those numbers are for. Sorry. Okay. So now I'd like to discuss another class of groups that is acting on A2 tilde buildings, but not A2 tilde groups. So in the paper by Ronan and others, there are 4 groups that act on A2 tilde buildings, and this is a presentation. So first of all, as I said, each of the 4 groups act on some A2 tilde building so that the quotient is just one triangle. And Ronan found those 4 presentations for some reason, but interestingly, he couldn't show, for example, G4 is an infinite group or not, and also he couldn't show if G4 really acts on some A2 tilde building with one triangle as a quotient. But anyway, so he managed to say if it acts on some A2 tilde building with one triangle quotient, then it has to be one of those. And by the theorem by Ponceau, they are Kazhdan groups. It acts on A2 tilde buildings properly and compactly. But Kazhdan constants are not known because it's not A2 tilde groups, first of all, and generating set is sort of different. Okay. And here's a list of properties. It turns out these 4 groups is studied by many people. in different contexts. For example, the second one, it turns out it's a triangle of groups in the modern language. So triangle of groups is so you start with a triangle, and you give a group to each vertex. You give a group to each edge, and you give one group to the triangle, and you do two-dimensional version of Bass cell theory. And in this case, vertex group is a Frobenius group of order 21, which has this presentation. And edge group is Z over 3Z. And the face, two-cell group is trivial. So there are four possible ways for you to include Z over 3Z in. Okay, sorry. There are finitely many ways for you to embed Z over 3Z into the vertex group, Frobenius group of order 21, and you try all possible ways to include a vertex group into edge group into vertex group, and you get at most 4 possible isomorphism type for the whole group. So Ronan didn't see this group from that viewpoint, but you can see it from the viewpoint of Hefliger, of a complex of groups. And also A2 tilde, a group acting on A2 tilde building as a lattice, it's automatic groups in general by Garrison and Short. And it turns out, interestingly, those 4 groups have the same growth function. That was proven by Floyd. There is a denominator. But anyway, so those 4 groups are not isomorphic to each other, but they have the same growth function that was found by Floyd. Okay, they have property T because they are acting on A2 tilde building as a lattice. G1 and G3 are linear, that found by those 3 people. They found a way to embed G1 and G3 respectively into GL3 of something. So they are linear. And G2 and G4 are not arithmetic, that was found by Teets. G1 and G2 are perfect group, that found by those 3 people too. And this is also interesting part, which is a recent progress they made. So G1, G3 are linear, but it's only recent that they found that G4 is not linear by showing this gamma 2, a subgroup of index 3, is not linear using, it's a hard theorem. I attended the talk and also tried to read the paper. It's not easy. But they finally managed to, actually Teets was asking if gamma 2 was linear or not, but Bader, Kapras, Crow managed to show they are not linear.
Could you say again why lattices and A2 tilde buildings all have property T? Is it just, are there links? The link has lambda 1 bigger than a half to it?
Why? Sorry, it's acting on A2 tilde building, but it's not A2 tilde group. You're asking
I'm
why?
just wondering about the link. I'm wondering about the links. The link, it's a Zooks link condition or whatever applies.
Right. Yes. 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 For example, yes.
Even though, but they're
Yes.
only.
So the theorem by Ponsu and Zook, they indicate a way to choose a generating set S. And not only just choose one generating set, but they exactly pin down the property, what S has to satisfy, and this natural one doesn't satisfy that property.
It doesn't.
It doesn't. It doesn't.
One has to use a different generating set.
Say it again?
So it has to use a different generating set.
Yes. Yes.
So then you get different. You come up with the same links.
And also there is another point. So remember the quotient is a triangle. There are 3 vertices. A2 tilde group, the quotient has to have only 1 vertex.
I don't care how many vertices there are. That's fine. I mean, it's the triangles of groups.
Okay, I see. So if you look at the paper carefully, generating set has to contain at least one vertex stabilizers. Okay, and in this case, it has to contain these Frobenius groups of the order 21. Okay, but I have only 3 elements or 6 elements there.
Right, I see. I understand.
Okay, so here's the computation. For those 4 presentation, I computed, and I get exactly the same numerical bound. Okay. And this is the part I'm most proud of. Eventually I noticed that this number is this. Okay, so of course, when I try to certify, I have to get a little bit, number a little bit less than those, then it's not exactly the same. But of course, I strongly believe that this is really the spectral gap, and it has to be this. Sorry, spectral gap is for this. If you plug it in, you get this number, and we do not any explanation. We don't know why or if those 4 groups have the same spectral gap or Kazhdan constant. Okay, now I take a look on the SLLZ. So here's the result. So we managed to get a number, lower bound of Kazhdan constant of SL3Z and SL4Z with respect to elementary matrices. So Netzer-Tom managed to find a lower bound for SL3Z, which was this number, which is much bigger than any lower bound that was known. The one I compare here is the one by Kasabov, and also there is an upper bound by Zook and other people too, but this is the one by Zook. So their bound is closer to this one than that one, so it's pretty good. But ours is slightly better. What is a little bit surprising to me was that our bound for SL4Z was bigger than our bound for SL3Z. Okay, but asymptotically, it should decrease if any increases. Of course, I'm not saying, remember, I first fix the range of BIs. So the range of BIs is just word length at most 2. So in that range, I can say for sure that epsilon is less for SL3Z than SL4Z, but I'm not saying that it's too early for me to say, and I think it's going to be wrong too, that the Kazhdan constant for SL4Z is bigger than the Kazhdan constant for SL3Z, I think, but I don't know. Okay, now that was the end of the infinite groups. So I also try to compute Kazhdan constant or spectral gap or lower bound of those for finite groups. First, I tried finite Coxeter groups. So I tried all of the classes, because in the first several of those, like 8 of those. In this case, AN is a symmetric group. Okay. So for this one, Kasabov both knows the Kazhdan constant and also the spectral gap. And as you see, there is a slight gap in between. So there is no equality in that basic inequality. Okay? But our numerical bound for epsilon is exactly again same. So our computer experiments is doing very well for finite Coxeter groups. Okay. Okay, then I was happy, so I went to finite complex reflection groups. So first of all, you can define complex reflection in this way, and again there is a classification of finite complex reflection groups, and there is a presentation. So I try to compute the Kazhdan constant and the spectral gap, I mean lower bounds again. Okay. Oh, I see. So there is no table. So, but one difference from the real case is that Kazhdan constant and the spectral gap are not known. Okay. So we just get some numbers for spectral gaps. We believe we are getting the spectral gap, but we don't know. And also, but there is some lower bound of Kazhdan constant, which is given by Wagner for some class of complex reflection groups, and comparing and thinking about together with our bound and his bound, it suggests that there is also a gap between gap in that basic inequality, as you observed in the real case here. So anyway, okay. So that is the end of the presentation of the numerical results. So those are natural problems I wanted to ask. Well, most of them are asked. So for those Ronan's 4 groups, Kazhdan constant is going to be equal to that one, or spectral gap going to be equal to that one. That is a natural question. So I said, so we get the candidate for a lower bound of Kazhdan constant here. So getting an upper bound of Kazhdan constant is sometimes easy, because you just need to find one representation without non-zero fixed vector and one unit vector, so that that vector is moved at most this number. So getting an upper bound, if you think of about the definition, getting an upper bound is easier. So if you manage to show that the upper bound is this one, then our lower bound is just numerical, but you can believe that this really is a Kazhdan constant. So maybe you have a chance to show, in that sense, this is a Kazhdan constant. Okay, second question is, as I said, is the Kazhdan constant for SL4Z bigger than SL3Z or not? Third question is, okay, so I didn't present the numerical results, but finite complex reflection groups, we get some numbers for epsilon, and is that going to be the number for the epsilon? In that case, and the last question, it's same for the Kazhdan constant, but Kazhdan constant, in the definition you take inf, so there is no way, is it not true maybe, that there's, this inf is really achieved. Also for epsilon, it is not clear if the spectral gap is achieved in the definition, but it turns out you can say for A2 tilde groups, in fact the spectral gap is achieved. So I wonder why, or under which condition spectral gaps or Kazhdan constant are really going to be achieved. So that's a question which I thought of after during this experiment. Okay, so that's it. Thank you.
What do you mean by achieved?
Oh, achieved, okay. So for spectral,
By definition, spectral gap. It's an
sorry, the soup. Sorry,
It's
it's,
yeah, it's a soup.
yeah. Okay, I'm asking if the spectral gap is achieved or not. A spectral gap, not the. You take this.
Yes.
Yeah.
On your last slide, why, I'm so sorry.
Last slide, okay.
Why are you saying when you relate to SLNZ, it must be at most 18?
Oh, okay. You're asking about this one.
Yes.
Okay.
So you mean N
n, yeah. Okay, so we get this number as a lower bound of Kazhdan constant of SL for z. Okay, on the other hand, Zook has an upper bound. So if n is bigger than 18, his upper bound is smaller than our lower bound.
So maybe you know that two of those Ronan groups, they are commensurable with two of A2 tilde groups. So
Okay.
did you try to exploit this? It kind of brings us to the next question. Do you know how to estimate Kazhdan constants for the subgroups? For example, if you have A2 tilde group, so the smallest one, for example, has a very nice subgroup of index 2. So,
Okay.
for example, can you, using your method, estimate the Kazhdan constant for a subgroup of index 2?
Oh, I see. So ask that question to a mathematician. Sorry. So in this experiment, I'm not using any of those things. You just give me a presentation, then I
Okay.
compute.
Okay, then maybe it's a good idea, because one could maybe, so you, for the presentation, you can kind of try of computing, because this would be a way to look saying at your things with Ronan groups, because saying in Ronan group there is a subgroup of index, okay, maybe quite big, something like 49, which coincides with a subgroup of index 3 in one of A2 tilde groups.
Okay.
Right, so there is a very nice presentation.
Yes.
So if you manage to construct this presentation, then there is maybe a way to prove exactly what is the Kazhdan constant for Ronan groups. Okay, maybe we should discuss it later.
Okay.
You don't know what Kazhdan constants do for finite index?
For finite index, no, but he said that with the presentation, he knows how to catch it.
Okay, so first of all, if you talk about Kazhdan constant, you have to specify the general descent. So you're asking about index 2 subgroup. So is there any natural way?
Yeah, I know the natural way, so it's
Okay.
like they are generated by 7 from x0 thing to s6, but there is a subgroup of index 2 which is generated by x0 and x1.
Yeah. Okay. My guess is, if you know the Kazhdan constant for, say, bigger group, you will probably you will have a lower bound of the Kazhdan constant of the small ones.
It would be great, because actually...
Yeah, but no, it's not going to be the Kazhdan constant.
No, but it's by, like you say, ask a mathematician, and I was discussing this at length with all three authors of
Okay.
of this book which you mentioned in the beginning, and then they discussed it by themselves, and
Okay.
they didn't know the answer. So there is no theoretical answer. That's why it's very interesting that you have some numerical methods.
I mean, to go from finite index to go to...
Yeah.
I mean, you can relate Kazhdan constant to finite index.
Okay, we can discuss this if you can.
Roughly, not in a sharp manner.
No,
Not
sharp
in-
manner, we
not
don't
in a
really need
sharp
the sharp
manner,
manner, but at least
You can
little.
show, yeah, you can relate the two.
We can discuss it later, because actually what is the upshot in the book of three courses, there is even a theorem where it says finitely many orbits, but then to compute, so it doesn't need this simply transitive action which was now mentioned, but then what happens when you start to figure it out, when you start to compute, you realize that the condition of the theorem is equivalent to having simply transitive action. So it's, yeah, I investigated it because I'm really motivated. I really want to know this concept.